Today we're going to cover section 3.4, Relations and Functions. A relation is a set of ordered pairs. The first element in a relation is called the domain or input, and the second element in the relation is called the range or the output. We're going to do an example now, building a table, and then from that table we'll make two separate relations. So we're going to fill this table about states and average fine by making up some information. So let's say that in Connecticut, you have an average fine of $200 for going 15 miles an hour over the speed limit. In Oregon, your fine is $145. In Utah, your fine is also $145. In Iowa, your fine is $90. In Kansas, your fine is $30. So let's build two relations from this data. The first relation, we will call it relation A, is going to be the set. These brackets let us know that we're going to deal with a set of the following ordered pairs. My input or domain value will be the state. My output or range value will be the fine. My second relation, relation B, I'll make the average fine my input value and the state will be my output value. So we'll have $200 Connecticut, $145 Oregon, and so on. Okay. Again, relation A is a set of ordered pairs. Relation B is a set of ordered pairs. Let's look at the domain for relation A. The domain of relation A is going to be all its input or first elements. In this case, Connecticut, Oregon, Utah, Iowa, and Kansas. So we say that the domain of relation A is going to be Connecticut, Oregon, Utah, Iowa, and Kansas. The range or output values of relation A is going to be all your second elements. In this case, $200, $145, $145. Notice that we have two elements with the exact same value. You only write it once. $90, $30. So the range for relation A will be $200, $145. Remember, I only need to write that once because it's not a different number. $90 and $30. Let's look at the domain and range for relation B. The domain of relation B is going to be that $200, $145, $145, $90, and $30. Recall, we only need to write $145 once because it's the same number. So I write $200, $145, $90, $30. And the range of relation B is going to be Connecticut, Oregon, Utah, Iowa, and Kansas. Connecticut, Oregon, Utah, Iowa, and Kansas. Now remember, or recall, we just said a relation is a set of ordered pairs. The domain is the first element in each one of those ordered pairs, and the range is the second element in each one of those ordered pairs. Now let's talk about functions. A function is a relation where each element in the domain corresponds to only one element in the range. So a function is a special type of relation where each element in the domain corresponds to only one element in the range. Now let's look at a different way of viewing relation A and relation B. Okay, here's relation A, and I'm going to draw it this way, as two little circles. This will be the domain of relation A and the range of relation A. Recall, the domain of relation A is Connecticut, Oregon, Utah, Iowa, and Kansas. And the range of relation A is $200, $145, $90, and $30. Now, when we are in Connecticut, we know that we will get a fine of $200. So Connecticut maps to $200. Oregon maps to $145, as does Utah, Iowa to $90, and Kansas to $30. Let's look at relation B. Same thing, two circles, one with a domain and one with a range. Recall the domain for relation B is $200, $145, $90, and $30, and the range for relation B is Connecticut, Oregon, Utah, Iowa, and Kansas. $200 mapped to Connecticut. The input value of $145 maps to both Oregon and Utah. $90 maps to Iowa, and $30 to Kansas. The picture view here that we have is just going to help us understand the definition of a function that we have above. Now, what we said was a function is a relation where each element in the domain corresponds to only one element in the range. Let's look at it as something that is not a function first, so we can get a better understanding of this definition. Let's look at relation B. Relation B is not a function. Relation B is not a function because the input value or the domain value of $145 corresponds with two separate range or output values. $145 corresponds to both the state of Oregon and the state of Utah. Okay? I like to think of this as a computer. If I were to ask a computer a question and the computer could only respond in a one-word answer, if I say, "Computer, I have a $145 ticket, what state was I in?" the computer wouldn't know what to tell me. The computer would want to say, "You're either in Oregon or Utah," but it couldn't give me a definite answer. The reason it couldn't get me a definite answer is because, again, my input value of $145 maps to more than one range value. That makes it not a function. Okay? Let's look back at relation A and determine if relation A is a function. Well, notice here, each domain value only corresponds to a single range value. Okay? Again, if we look closely, both Oregon and Utah have a range value of $145, but if we think of it in terms of the computer example, if I ask my computer, I'm in the state of Oregon, how much money would I have to pay for my fine? The computer would say $145. It wouldn't have an issue trying to determine the amount that's due because the state of Oregon only maps to $145. Likewise, if I say, computer, I'm in Utah, how much money am I going to pay? It's going to tell me $145 because that input value, Utah, only maps to one output value. So this is a function. So again, a function is a relation where each element in the domain, so each input value, only corresponds to one output value. Okay? Every time that I say I'm in the state of Oregon, I know that I have to pay $145. Every time I say I'm in the state of Kansas, I know I have to pay $30. But again, if we go back here and look at relation B, if my input value is $145, the computer isn't going to be able to tell me whether or which state I am in. Let's do some examples now, determining if each given relation is a function. The easiest way to determine if these relations are functions is looking to see whether or not an input value repeats. So in my first relation here, I don't have an input value that repeats. Every one of these input values is different: 10, 6, 2, and -2. Because nothing repeats, I know that it's very easy and I can say, yes, I am a function. Let's look at the second one. In my second one, I notice that my input value of 3 repeats. The first time 3 corresponds or is mapped to 4. The second time 3 corresponds to 5. Well, again, if I were to say, computer, my input value is 3, what should my output value be? My computer wouldn't know what to tell me. It would give me an error because the number 3 is mapped to both 4 and 5, which means my input or my domain corresponds to more than one range. So this is not a function. Okay, let's look at J, and we're going to change J a little bit. We're going to add another ordered pair to J. Okay, so now we're going to see I do have a repeated input value. My repeated input value is 6. But notice, every time that the number 6 appears as an input, it has the exact same output value that it did before. So if I tell my computer my input value is 6, my computer is going to say your output is 8, because 6 always corresponds to 8. So just because your input value repeats doesn't mean that you're not a function. Only when your input value repeats and is something different for your output value are you not a function. So J down here is a function. Our last one, relation P, we have repeated inputs with different outputs, so we are not a function. Great. So thus far, we know a relation is a set of ordered pairs. Domain are the first elements in those ordered pairs. Range is the second element in those ordered pairs. And a function is a relation where each element in the domain corresponds to only one element in the range. Let's continue to look at different things for functions. Function notation. Function notation is another way of writing an equation. It lets us designate an element in the range of the function. So before we may have seen y equals 3x plus 5. Well, now instead of seeing y equals 3x plus 5, in function notation we would write f of x is equal to 3x plus 5. So in order to get an equation into function notation, we would replace y with this f parentheses x, close your parentheses, and the way that we say that is f of x. Again, what this does is this gives us the value of the function at x. To find the value of a function at a given number, or let's say variable or expression, we substitute that number or variable into the equation and evaluate or simplify. Let's try that again. Evaluate or simplify. So let's find the following function values. For f of x is equal to 3x plus 7. We are to find f of negative 3, f of 0, f of 2, and f of x minus 1. So the first one, f of negative 3. What f of negative 3 is telling us to do is to substitute negative 3 everywhere there was an x in my equation above. So instead of writing 3x plus 7, well, now since x is negative 3, I write 3 times negative 3 plus 7. So I have replaced that x with negative 3. If I clean this up, I get negative 9 plus 7, or negative 2. So when my input value is negative 3, my output value is negative 2. This is actually representing the ordered pair negative 3, negative 2. Let's find f of 0. F of 0, same thing. What we do is instead of writing my x here in my equation, I write 0, and then I evaluate. So f of 0 would be 0 plus 7, or just 7. Again, if I were to think of this as an ordered pair, my input value is 0, my output value is 7. So this is saying when the function has an input of 0, the output value would be 7. Let's find f of 2. F of 2 tells me instead of writing this x, I write 2, and then I clean up. So f of 2 is equal to 13. So if we were looking at this as an ordered pair, it would be 2, 13. Alright, the last one I want to look at is actually substituting the expression x minus 1. This is no different than anything we've done before. Instead of writing this x here, I'm going to write what's in this parentheses, or this x minus 1. So I'm going to write 3, and again, instead of writing x, I would write x minus 1 plus 7. And now I need to simplify. So distributing, I get 3x minus 3 plus 7, or f of x minus 1 is equal to 3x plus 4. Okay? So now I have evaluated or found the values of the function at each one of those given ones. For the next examples, I'm just going to find for this one f of negative 3 and also the f of x minus 1. For the next one down, it'll be f of 0 and f of x minus 1, just to kind of save time. Okay, let's begin with f of negative 3 for this example that we have. Well, f of negative 3, recall, that means to substitute negative 3 in for that x and evaluate. So this becomes negative 2. Recall that negative 3 squared is a positive 9. So f of negative 3 is going to end up equaling negative 17. Okay. Now let's find f of x minus 1. Well, this is going to tell us to substitute that x minus 1 in place of that x there. So we say negative 2 times x minus 1 quantity squared plus 1. So f of x minus 1 is negative 2 times, well, x minus 1 squared. If it helps, write it twice and then distribute so you don't make any mistakes. Let's go ahead and distribute these. I would get x squared minus 1x plus 1, which becomes x squared minus 2x plus 1 when I combine like terms, plus that other 1. Don't forget to write that down. Now I'm going to distribute this negative 2. f of x minus 1 is equal to negative 2x squared plus 4x minus 2 plus 1. Finally, combining like terms would give me negative 2x squared plus 4x minus 1. So f of x minus 1, for this f of x equal to negative 2x squared plus 1, is this negative 2x squared plus 4x minus 1. Okay, what we did there again is just like we did in everything else. We substituted x minus 1 for the value of x in our given problem. Right, for this one, let's find f of 0 and that f of x minus 1. Okay, again, f of 0 just means instead of writing all these x's, I'm going to write 0 instead. So this is 0 squared minus 2 times 0 plus 3. So evaluating or simplifying here, I'd get 0 minus 0 plus 3, or just 3. Okay, now let's look at f of x minus 1. And f of x minus 1, instead of writing this x, I write x minus 1 squared minus 2. Instead of writing that x, I write x minus 1 plus 3. And now I simplify. Again, if it's helpful to you, I would write this out as x minus 1 times x minus 1 so we don't forget to distribute. Let's distribute this negative 2 here, negative 2x plus 2, and don't forget to bring down your plus 3. If I multiply x minus 1 times x minus 1, get the same thing I got before. It would be x squared minus 1x gives me minus 2x. Negative 1 times negative 1 is a positive 1. I'm going to write everything else down. If I combine like terms, I end up with x squared minus 4x plus 6. Hey, for my last one here, I'm going to find f of 2 and also that f of x minus 1. So let's find f of 2 first. Okay, just like we did in every single one of this, when we're finding a function value, we replace what's in parentheses in place of our x, or our variable in our function. So this will be 3 over, instead of this x, I write 2 minus 1. So f of 2, it becomes 3 over 1, or just 3. Let's find now f of x minus 1. f of x minus 1 would be 3 over, now instead of that x there, I need to write what's in my parentheses, x minus 1, but I can't forget about the other minus 1 that I had. That doesn't go away. Again, when we find a function value, we replace what's inside parentheses in place of our variable and copy the rest of it down, so that minus 1 had to come along as well. If I simplify this result, by combining like terms there, I end up with 3 over x minus 2. So f of x minus 1 here is 3 over x minus 2. Okay, so we've talked about relations, domain, range, functions and function values, and function notation. The last thing in this section that we will look at is the difference quotient. Now the difference quotient, which will always be given to you, is equal to f of x plus h minus f of x all over h. Okay? In order to find the difference quotient, what I typically do is kind of look at it a piece at a time. Okay? So let's find the difference quotient for the next three examples here. The difference quotient will come up again if you take pre-calculus, or if you take elements of calculus, or if you take calculus itself. It'll become the derivative, and you'll see that, or where the derivative definition comes from. So, for our first one, f of x is equal to 3x plus 7. If I want to find the difference quotient for this, I need to figure out what f of x plus h is. Well, that is finding a function value, which we just did. So that means instead of writing this x right here, I need to write x plus h. So this is 3 times x plus h plus 7. That is what f of x plus h is for my function. But I'm not done, because the difference quotient contains other pieces. It then tells me to subtract f of x. Well, I need to subtract f of x. Well, f of x is what was given to me, that 3x plus 7. And then I end with putting this all over h. Okay? Well, let's distribute and simplify and see what we get. I distribute here, and I get 3x plus 3h plus 7. I distribute this negative, and I end up with minus 3x minus 7. And this is still everything over h. If I start looking to see if there's any like terms that will combine in my numerator, I realize that my 3x's cancel, as do my 7's. So I'm currently left with 3h over h. Well, my h's will cancel, so my final answer is 3. So the difference quotient for 3x plus 7 simplifies to 3. Hint, at this step here, if everything that doesn't have an h cancels, so if you move along here and everything that you have, every term in this numerator doesn't have an h, you did something wrong. Let's look at our second one. Let's find the difference quotient for negative 3x squared minus 4. Okay? Again, the first thing I need to do is find f of x plus h. Well, that tells me instead of writing x squared, I need to write x plus h squared. So this becomes negative 3x plus h squared minus 4. That is f of x plus h. Again, after that, I need to subtract f of x. Well, f of x was my given, so I need to subtract that negative 3x squared minus 4. And this all goes over h. Okay, right? So we need to square x plus h squared. And I'm going to square that on the side just in order to save room. If I take x plus h and I multiply it by x plus h, right, because this is x plus h squared, it becomes x squared plus xh plus xh plus h squared. If I combine like terms, I end up with x squared plus, that's 2 xh's plus h squared. I would memorize that x plus h squared is equal to x squared plus 2xh plus h squared. Okay, so let me go ahead and write that information down. I'm going to bring down my negative 3. Recall that x plus h squared we just determined was x squared plus 2xh plus h squared. And then I need to subtract 4. If I distribute this negative here, I end up with plus 3x squared plus 4 all over h. Let's go ahead and distribute the negative 3 in here. I end up with negative 3x squared minus 6xh minus 3h squared. Still have that minus 4 plus 3x squared plus 4. All of this over h. I'm going to move that right here. Let's see what, if anything, cancels. Well, I have a negative 3x squared and a positive 3x squared. Those will cancel. Right? Nothing cancels with this negative 6xh or this minus 3h squared. But I have a negative 4 and a positive 4. Those will cancel. And again, I need to put this all over h. Notice when I got here, each one of these terms has an h in it. if every one of the terms in my numerator did not have an h, I did not do this right. So now I have to reduce. Well, I can factor an h out of my numerator. If I were to factor out an h from negative 6xh, I'm just left with negative 6x. If I factor out an h from negative 3h squared, I'm left with minus 3h. And this is now all over h. Well, these h's will cancel, so my final answer will be negative 6x minus 3h. So the difference quotient for negative 3x squared minus 4 would be negative 6x minus 3h. Our final problem is negative 2x squared minus x plus 1. So again, the first thing we need to do is find f of x plus h. That means to plug in an x plus h for each one of those x's. So I write negative 2 times, this becomes x plus h squared minus x plus h plus 1. So that's my f of x plus h. Then I need to subtract the f of x. I need to subtract the given, minus that negative 2x squared minus x plus 1. And again, we put this all over h. So the difference quotient is always going to be f of x plus h. So I'm plugging in x plus h everywhere there was an x in my given. Then I subtract my given, and I put everything all over h. So let's go ahead and distribute, combine here. Remember, x plus h squared is that x squared plus 2xh plus h squared, right? If it takes you a while to figure that out, I would memorize it. So this is going to be now negative 2 times that x squared plus 2xh plus h squared. Okay, if I distribute this negative sign, I end up with minus x minus h, then my plus 1. If I distribute this negative sign, I end up with plus 2x squared plus x minus 1, still everything over h. Let's go ahead and distribute that negative 2. If I distribute this negative 2, I have negative 2x squared minus 4xh minus 2h squared, and then there was that minus x minus h plus 1 plus 2x squared plus x minus 1, everything over h. So I distributed up to here and then just copied the rest of it down. Let's see if anything cancels. Remember, everything that does not have an x in, everything that does not have an h in it should cancel. So I have negative 2x squared, and that's going to cancel with a positive 2x squared. Negative 4xh doesn't cancel with anything. Negative 2h squared does not cancel with anything. Negative x will cancel with my positive x. Minus h does not cancel with anything. Positive 1 will cancel with my negative 1. And this now becomes all over h. Again, notice every value that I have up here in my numerator has an h in it. Every term has an h in it. Okay? I'm going to move this right here. I'm going to factor an h out of the numerator. If I take an h out of negative 4xh, I'm left with negative 4x. If I take an h from negative 2h squared, I have minus 2h. If I take an h from an h, I'm left with a minus 1. Remember, you have to be able to distribute that h back in and come up with what you just factored. Okay? This doesn't go away. Because the h isn't there, there is a 1 as a placeholder. Remember that h has a 1 as its coefficient. Okay? Its coefficient is 1. We put this all over h. Well, our h's cancel. So the difference quotient here would be negative 4x minus 2h minus 1. Right? So for this section, we learned about relations, domain and range, functions, function notation, finding function values, and finding the difference quotient.